Um, yeah. Thank you for agreeing to meet with me. I'm really excited to speak to you. We had a lot of interesting questions about your research, your work at UMD and at Apple. So just wanted to learn more about you. Can I address you by Dr. Vemulapalli?
Yeah, I mean, you can call me Ravi. That's good. That's okay.
Okay. Ravi. All right. Yeah,
Yeah,
well, great
yeah.
to see you and speak to you.
Wait,
Um,
I don't know. How important is it to record this? Just
sorry, I was just interested in recording this so I could publish it to some of my friends if they were interested.
okay.
Um,
I don't know. In a
but
sense, typically I'm a bit careful about recordings just to make sure. I don't know where it goes, what happens, and I don't know what we talk about. So
okay, no, that's fine. If there's sensitive topics that you're not interested in speaking about or you can't speak about, it's you don't have to.
okay,
Um,
yeah.
only whatever you're comfortable with,
Okay.
sharing. Right. Um, so yeah, just to get started, I was wondering if you could tell me a little bit about yourself and your journey in like computer science and AI, machine learning.
Cool. So yeah, I mean, like maybe I'll go back from here towards backside rather than. So currently I'm working at Apple. It's been like around 2 years, and before that, I was working at Google for about 6 years or so. Prior to that, I did my PhD at UMD, and throughout this entire career, I'm mostly working on topics around machine learning, AI, computer vision stuff. So, and prior to my PhD, I was back in India. That's where I did. I mean, I was born, brought up. I did my schooling till undergrad there, and
Right.
there I was doing my actual undergrad in electrical engineering. Even here, I did my PhD in electrical engineering department, though I was just doing mostly AI vision stuff. So I think I got interested in all these things back in undergrad. That's when I initially started doing some small projects or playing with images and stuff. So that's how I got interested in this topics. I think this field was not this hot or this big at that
For
time.
sure. Hmm.
Over
Yeah.
the last, I don't know, 10 years, things have changed drastically. But yeah, that's how I got started during my undergrad. And then once I got interested in images and stuff, I did some projects which made me more interested in those things. And then I decided to do a PhD and then
Mhm.
came.
Right. Yeah, that's really interesting. Was there like a specific event or anything like, that you can like point out that was really key in, directing you to working with vision and images, or was it just through the natural process of schooling?
Yeah, I wouldn't say there was any, I don't know, big key moment. It was mostly like how I don't know, maybe inherently, I think I was generally interested in visual modalities. So typically, if you talk to folks working in machine learning, you can do machine learning on different things with images, audio, or even health biosignals. I mean, it's all sort of end of the day some machine learning models, but the input data varies depending upon what applications you're interested in. I guess personally, I was interested in images in general, so I started playing with images and slowly got in there. I wouldn't say there was any
Right.
big key thing. It's mostly, I
Mhm.
guess, small projects, my interest in visual modality. So that's how I got started.
For sure. Yeah, that's really interesting. So touching back on that research aspect of things, so one of the papers that we were really interested in was the one that you recently published, the one that I think ICML is the one happening right now. I think it's titled it's regarding vision foundation models. I was wondering if you'd be open to giving a simple overview on that research.
Yeah, definitely. So actually, yeah, okay. By the way, before I don't know how this goes, but actually, I was more interested in also knowing what your club,
Oh,
and
sure.
how you guys operate, or like, do you guys follow this latest stuff? And
Right. So I'd say we during the school year we meet about once a week or sometimes with stuff it ends up being once a month about. But throughout the club we love to read papers and we're all active in the high school uh I mean there's coding competitions that typically happen. It's all just like a general interest in computer science and as we know, AI is like the big thing in computer science now. So yeah, just reading recent papers, looking up videos. Andre Karpathy releases a lot of amazing
Yeah.
videos online. So, watching all those interesting videos and learning about it by ourselves. And we were interested in your work, so that's what we
Hmm.
contacted.
How did you guys come across this?
Oh, this research, it's interesting because we were also very much interested in vision models. And I know you referenced that you're taking the vision models for training of smaller
Yeah.
models. And recently we came across this paper when just looking throughout, uh, images and vision, and I don't know, we just thought it was very, very fascinating, and we wanted to learn more. So.
Cool. Yeah, definitely. Okay. Yeah, I can talk about it more. So maybe, I mean, I'll give you a bit on the motivation why we were doing that work so that I don't know, you may find more interesting once you know
Okay.
why it is being done,
Yep.
just rather than what it is being done. So if you have following the field, yeah, you might be seeing that there are like a lot of progress happening now, but the biggest trend in the field is becoming big. I
Mm,
mean, big models, all this, I think corporate companies are building big models
right.
which are being built with a lot of data. And the bigger you go, the more data you use, the more compute you spend on training a model, the model ends up being a better model. So it's a sort of, I don't know, very well established trend in the field now.
Right.
Everybody is going big, but which is good to an extent because yes, you're solving more and more problems. But then I guess it puts field in a place where maybe only those who can afford that compute can build those models. And especially once you build those models, more important thing is when you serve those models to people. If you want to use those models
Mhm.
in different use cases, different applications, that gets very costly. For example, many of these models, you may not be easily put it on devices, or you may not be able to just throw them everywhere because it might end up being costly. So, and also in many scenarios, actual real world use cases, many times you want machine learning systems to solve one particular thing. It's
Right.
not like
Domain, like
domain.
domain specific.
Example, you have, I don't know, a surveillance camera, it does particular things, that's all. If it is good at that, that's a good product.
Right.
It doesn't need to do everything in the world. So maybe we don't really need these big models whenever we are interested in particular application. So I think that's why it is, while big models are being built, the community is going in that direction. It is also important actually if you want to use them in real world to focus on the other direction where I want small models which
Mhm.
will do a particular set of tasks wherever it is being deployed as good as they can. Now, if that is the goal, you may ask this question, oh, I'm interested in a small model which does something very well. Then all these big models which can do many things, are they irrelevant to me? Because I'm not interested in big models. So this brings us the question, okay, they are not useful to you to, to put it in the application, but then maybe they are useful to you to build your model.
Right.
That's the whole theme of this work is that, oh, I have all these big models, everybody is building them. How can I use these big models to train my small models as best as I can with as little data as possible? So that's the whole theme of the work.
Right. To be environmentally efficient and save on the compute by using smaller amounts of data from the larger model to train the
Yeah,
smaller
so
model.
it's in the two axes, which is the whole focus is like efficiency. And there are two
Mm,
types of efficiency. One is, of course, compute efficiency, which is you want to train them using as less as compute as possible. And of course, because they are small, naturally, when you use them for applications, they will also use less compute.
right.
And the
That
other
was
thing is data
go ahead.
efficiency. The data efficiency is when I'm trying to train a model for a particular task. Usually, I need data to teach the task. And
Mm,
if I need a lot of data, again, collecting data, getting that data might be, I don't know, costly. It may involve whatever, some data collection process, either costly or time consuming. So if I can do this training with less data, again, I'm gonna save something, either time, money, and however it translates to the data. So both aspects, compute efficiency and data efficiency, are sort of considered here.
Mhm.
Oh, you had a question? What was it?
Oh, no question. No, I was just gonna say that that was one of the interesting ideas that we were wondering about, like how you would balance, the impact, the efficiency of the model with the robustness of the model, and I think you answered that pretty well.
Yeah.
So, um, an add-on to that would be, what are some of the like key challenges that you tackled, and what would you say like would be one or two of your most key findings within that
So
paper?
that's the thing. So now that since the groundwork is done, you understood the problem, the motivation. So now, okay, like then the question we asked is, okay, what is the best way I can use these big giant models I already have to train the small model, right? So and then we explored different strategies, and few sort of findings were this. Maybe I can even explain this nicely in English, which is okay. Imagine this big model is fine. It's a big brain. It
Mhm.
has been trained with a lot of data, which means it has seen a lot of things and it accumulated a lot of knowledge. That's good.
Yeah.
But
Mhm.
then my small model, because it is small, it's a smaller brain. It doesn't have as much capacity as the big model.
Right.
So if I try to transfer some knowledge that the big model gained to the small model can't learn everything. It's like, I mean, again, it's like a teacher-student setting. Teacher may be,
Right.
I don't know, smart, but the student with limited capacity, they can't really get entire knowledge from the teacher to the student.
Right. Right.
Then if that, because of the capacity, but I'm not interested in the small model doing everything the big model can do. I'm only interested in it doing some particular things. So one key insight is that when you're transferring, trying to knowledge from the big model to small model, you only focus on that knowledge that is useful for the small model's job.
Right.
Whatever that is sort of, I would say, it's like a subset of the big model's knowledge. So
Yeah. Yeah.
it's sort of
Mhm.
so that the small model can learn. So that is the key. Okay, focus only on the knowledge that is relevant for your task. And similarly, I don't know if you are familiar with this notion of knowledge transfer or knowledge distillation between models. Is that something that you are familiar with? Have you heard about it before?
I've definitely heard about it, but if there's like any clarifying or like like just one sentence summaries about it that you'd like to provide.
It's almost at a super high level. This whole notion of distillation or knowledge transfer that exists in the machine learning community is literally by training a model by mimicking another model. So
Okay, okay. Yeah.
it's like this model will be trained with an input and an output, and the output to train this model is literally obtained by running the
Mm,
big model.
okay.
So
Mhm.
whatever the big model says, I'll just try to copy that, mimic that. That's
Right.
the whole framework of distillation. Now, that is what we also use in this setting, where
Mhm.
the small model learns from the big model by mimicking. But then there is the question of on what data should I mimic?
Mhm.
What I mean is, I mean, I can take the entire world images and ask small model to exactly do what the big model is doing on this, I don't know, entire web data. But then, as I said, it's not relevant to me. I'm only
Right.
interested in a particular task. So the other key thing is go on when you are mimicking big model, only mimic on those images that are probably relevant to your domain.
Okay.
So pick a data. So there are two things. Pick a data, that data which is relevant for your domain. And
Mhm.
on that data, the small model will try to mimic the big model. And what does it mimic? So there is a question of course, the big model as a neural network. So if you give it an image, it will extract different layers, will extract different features. You can
Sure.
mimic, I mean, try
Yeah, yeah,
force your
yeah.
model to mimic anything. So again, the key thing is if you just try to mimic any of these features, they don't do the best. So
Yeah.
what we do is take a small data of whatever task target you are interested in and use that small amount of data to teach your target task to the big model.
Okay.
So it's almost like this. I have a big brain trained on everything in the world. I will
Mhm.
slightly adjust that big brain to the task that I'm interested in. by
Mhm.
using small amount of data. Because I mean, it's more like the hypothesis is that big models have seen a lot of data.
Yeah,
So you want to teach a new thing to them, they can learn very quickly.
right.
It's
Because they already have all that information.
they have all that information. You just have to teach it that, oh, this means this, whatever. So
Mhm.
models with small few examples of your target task, you teach it to the big model. So big
Right.
models can learn that very quickly. Once they learn that using small amount of data, now we will train the small model to mimic big model's predictions
Mm.
of this task. Because now the big
Right.
model has been changed to do this particular task. So so effectively overall two aspects. One is I will teach big model first, and
Hmm.
then small model will mimic that big model,
Big
which is
model.
not my task. And also, in order to mimic, I need to decide a set of images because on these images, I'm going to mimic. And that
Okay.
set of images should also be curated according to your task.
Sure. Can you give an example of what something like that would be? Like,
Okay. For
what?
example, pick up one example from a paper. Let's say I am interested in, let's say, classifying some satellite images. I think that's one of the examples in the paper, which is,
Yeah.
let's say, my job is like I want a model which gets aerial views and then it
Hmm.
tries to classify it into some categories, like is it a crop region, it's a field, or is it a river
Yeah.
or a city or something. Let's say that's what I'm interested in. So all I want to do is to build a small model which does this very well. So maybe I can put it in a camera on a plane and just do aerial surveillance, something. That's it.
Yeah.
Now this is my task of interest. Now I can and I only have few example images for this. Let's say you have 10 different categories and you just have, I don't know, 5 or 10 examples from each one of them. And I have a small data set with me. Now, if I just use that small data set to train the small model directly, it won't work very well because that's like really few examples to train a model.
Right.
What I'm going to do, take this small data set, teach it to this big model which has seen a lot of images from all over the internet
Right.
with few examples that do a decent job of this task.
Sure.
Now I have a big model which can do my task. I'm going to train a small model for the same task of the satellite image classification.
Right.
And the way I train is I'll ask this small model to mimic the big model. But
Yeah.
now, as I said, whenever we say I'm mimicking, I'm doing distillation, I need to do it on some data of images.
Yeah.
That data of images, again, as I said, it's very important that this data of images is something that is related to your task. For example, if I'm interested in the satellite classification, and if I teach my big model to mimic small model on random images of cats, that's not going
Sure.
to do anything for me because it just learns to mimic on the images of cats.
Right. So you need the curated data set.
So we need a curated data set which looks a bit like my satellite images. But
Hmm.
then the key is, oh, I only have small set of satellite images with me. How can I get more? The thing is,
Yeah.
whenever you mimic, the more data you have on which to mimic, the small model will learn better. So
Right.
one of the things that we suggested in the paper is also, okay, you can potentially curate this data set by doing something like an image retrieval. So
Sure.
you use your small data set that you have with you, and then there are now large scale big data sets available which have been dumped from internet like billions and
Yeah.
billions of images. So you can take these small images as sort of query images and go and find if there are
Sure.
other images, similar ones from
Right.
this big pool. And another interesting thing that we did is it depends. I mean, let's say your big data set may have or may not have. What
Hmm.
if you don't have? I mean, of course, I don't know. Let's say if you go today and dump from internet, from Google search or what, maybe you get like 5 billion images. I don't know
Right.
how many of them will look like your satellite images. Maybe if there are a lot, good, you can get them.
Right.
But if there are not a lot of them, again, there's the question, how do I get them?
Hmm.
What we found one interesting thing is you may not have exact satellite images out there in that pool, but you
Hmm.
may have sub-regions of images that may look like.
Oh, okay.
So the thing is, at a picture, I think if you look at the paper, we even show one interesting example there where it's a totally, I think it's an image of some symbol or a medal or something.
I think yes, I think I know what you're talking about. Yeah.
But if you cut a region in that thing and change, I mean, you do some sort of augmentation of it by modifying the colors a little bit and stuff,
Right.
it suddenly look like a river, a satellite view of a river.
Mm-hmm.
So what we did is that which is okay, let's just not match images to images, which is what typically everybody does, typical any retrieval. What we said is, okay, let's take an image that I'm interested in satellite. Now I'm gonna search through all this big pool of images, but not at an image level. I might even search at sub-regions within an image. And I
Right.
may search by changing parts
Augmenting
of
the
it,
images.
augmenting the images. That way, there are my chances of finding matches increases significantly.
Hmm.
That's one of the strategies that we explored in this paper.
Right.
Yeah, yeah.
That's definitely interesting. Were there any attempts on like, taking the image and I'm not sure if this is something that's already happened, but taking the image and I don't know, is there like some other sort of model that can provide just like a similar idea of the image, like a zero shot model that'll take the image and alter it slightly, or is that not possible yet?
I mean, it would alter it slightly to do what?
To simply just like, augment the images. Are we already augmenting the
Yeah,
images
so
that
in all these things, we typically already augment. So whenever we train, I think it's almost like a default thing these days. Whenever I train a machine learning model, if I say I have a data set of 10 images, it's not exactly 10 because every time the model
okay,
sees these
yes, yeah,
images, you always augment them. So
right,
everything is already on top of the
right,
augmentation
right.
standard that happen.
Because you need more data to train them on.
Yeah, it's always you always need more data. The
Yeah,
easiest way to get is augmentations, but then yeah, whatever I'm talking is on top of it. You assume
right,
that you're already doing as all the
right.
augmentations you can.
Hmm. For sure. It's
Yeah.
definitely. Could you explain some of the like the real world applications where we could see some of this technology being used?
So I think it should be useful for any application where you build a vision system
Sure.
and scenarios. I mean, whether it is surveillance or I don't know, a typical standard image classifier or even like a medical disease. I think this satellite recognition. I think we explored few things in the paper, like yes, satellite image classification, some medical image classification, or some uh, typical natural image classifications like scene recognition. I think any vision system that you can think of which takes an image, gives out
Hmm.
some sort of classifications and stuff, you can use this system.
Hmm.
The overall ideology that I want to build a small model which is good for this.
Right. And one foundation model can generate multiple of these smaller
Yeah,
models.
yeah,
It
yeah,
just depends on that data set that you're
yeah,
curating
yeah.
it on and task.
Yeah, yeah. So it's just like we start from one foundation model, right? So this whole process spits out another new small model, and you can just do this again and again
Many
using
times.
different data, which eventually will give you a model for different tasks.
Mhm.
Yeah, yeah,
Right. Lots of applications then.
yeah, yeah. Lots of applications.
Mhm.
And one of the key important things I said overall with this, if you look at the paper, two things that we try to highlight is okay, I'm able to do all this and get a model which does something very well using small amount of data. Because I'm assuming that I only have small amount of data, we'll do this retrieval, we'll do somehow and augment the data. And the other thing is computationally in terms of training this small model, how much compute I spend to train the
Mhm.
small model. I think that is also, at least this strategy is much better than other things that people are doing these days. I mean, there are many other ways you train a model. Typically, small way, if you want to train a model and you only have small data set for your task, the standard thing people would do is they'll pre-train this model on something else
Mhm.
where there's a lot of data and then come and then fine tune it a little with your task. So there are tons of pre-training strategies available. And if you're familiar, or I can just say, a few years ago, ImageNet, the
Yes, yeah,
training
yeah, yeah.
model on ImageNet was the most popular one. Then training using like clip style, like image text contrast was there. Then there are a lot of self-supervised learning strategies. We compared with all of them in the paper, showing that all these well-established, widely used pre-training strategies, they end up being a bit more costly in terms of computation
Hmm.
than me just trying to mimic a big model.
Sure. Hmm. Oh, for sure. That Yeah, the savings on the computational efficiency and the just the generalizability of it make it a
Yeah,
very like effective
yeah.
idea. I did wanna one other question I had was there is a I mean you must know, but there is a wide interest on like fairness in like machine learning and AI. Um, did you explicitly touch on the important like how did you guys highlight or ensure that there was some level of fairness within the
So
data?
so I guess when we talk about fairness, I guess again the definition of it depends on the application scenarios. Most of the experiments we did, or most of the applications we considered, are typical outdoor natural images,
Sure.
where I guess there is not well established fairness, or people don't think too much about fairness in there because it's not really associated with people or any
Sure,
sense
sure.
of that. It just images that you capture in the scene. So I guess that's why we didn't really touch upon that aspect, because it was not
Oh,
important.
definitely for the applications that you're mentioning, it's not.
Yeah, but if we were working with, I don't know, things that do with people, faces, or I don't know, some other social aspects, then yeah, that gets very important.
Okay. Yeah, for
Though
sure.
one thing, I'll highlight one thing, which is when we said, so even though this was not focus, we did try to do something to have a notion of balance in the data set that we obtained by retrieval, because I mean, forget about this notion of fairness when it comes to people, but even in a standard, I don't know, data, any outdoor or even a, let's say, animal classification, there is another notion called imbalance. It may
Right.
not naturally, it's not like fairness, it's more like maybe some of the thing, classes may have more images, some may have less
Right.
images, there is imbalance in the data which may affect. So what we did is that, as said, right, we usually start with a small data set and we try to retrieve.
Yeah.
And when we retrieved, we tried to ensure that we are kind of retrieving equal number of images for each of my query, so
Hmm.
that if I start with a query set which is, let's say, balanced, we will usually end up with a bigger set which is also somewhat
Also,
balanced. So we made sure that we don't end up retrieving 1,000 images for one of them and then only 100 images for the other.
yeah. Hmm.
Even though this may have like very good 1,000 matches, whereas the other only had like, let's say, 100 matches, we'll just
Yeah.
only take it from here, something like that.
Hmm. Okay, yeah. That was definitely really interesting look on your research. And I did just have a couple more questions regarding your work. So, through what we've seen, I know you touched on natural language processing in
Yeah,
some of your work
these
prior.
days. Yeah,
Uh, and I think one of the questions that was brought up was, these are two kind of separate fields, so natural language processing and computer vision. But I think, as we see more multimodal things popping up, one of the questions that we had was, what potential, right, you being at like the forefront of all this, what potential do you see for I guess the cross-pollination between like natural language processing techniques and computer vision.
yeah. I think traditionally they were completely different fields. I mean, I was from a pure computer vision background. I knew nothing about NLP until recently. Even now, I wouldn't claim that I know a lot. I would say the other way, which is the field is moving in a direction where the boundaries are like blurred now. Just because
Okay.
the same models, that's where you see this multi-model, you are seeing so many multi-model works these days. I mean, people have been working on this topic of multi-model, I don't know, for 2 3 decades, but nothing significant happened there in the past because each modality remained as something separate.
Sure.
Each
Right.
of them were processed by their own stuff. But now I think with transformers, I think it was also earlier, let's say, even the neural network architectures used by different fields were different.
Right.
I think transformers, I would say that's the biggest breakthrough because
Hmm.
that is what is allowing people to unify everything because the model architecture has no notion of modality.
Right.
Uh,
Right.
It just takes tokens. As
Yeah.
long as you represent everything in the world in the form of a token or an embedding, that's good enough for the model. So I
Yeah.
think that is why these boundaries are blurring now,
Hmm.
and it does, everybody working in earlier who were working in different fields are now all merging, or people are doing more multimodal stuff. So I guess that's where eventually the future is gonna go. It will be
Right.
multimodal. I think even now it's there. For example, I mean, GPT is now multimodal, and all these models that are coming up from different companies, they are becoming multimodal because yeah, everything is represented as a some token, and
Right.
boom, it gets into the same model. So
Hmm.
I guess that is the reason why it's
Right.
happening now, is because of the
Yeah.
transformers.
Yeah, for sure. The yeah, the fact that like the Transformer is making everything the same,
Yeah,
there's a lot more collaboration. I think that's
yeah,
definitely one thing that's happening, and I think that that's really the key driver that's allowing all these people to
merge.
bring together. So I think just two more questions for you. So some of the stuff that we've also seen that you've done previously would was regarding like some probabilistic models. Would you say that you worked
A while ago.
a while ago?
Yeah, yeah,
Um,
yeah.
uh, I know probabilistic models are definitely not, in they're definitely there, but compared to transformers, they are
Yeah.
kind of separate. But how would you say, how do you see the role of like these probabilistic models like evolving in the era of deep learning?
Deep learning. So even if even the work that I did in that field of probabilistic models, which before the transformers was not purely probabilistic models, but I was actually trying to merge neural networks and probabilistic models.
Mm.
That was the work that I did because I mean, so the theme was that probabilistic models typically have, if you're using a probabilistic model, the way you infer those models is like an iterative algorithm. It
Right,
does several steps of iterative solving, and eventually you will solve the problem. It's almost like an optimization problem. Yeah, so and then it gives you an answer. The earlier they were very popular, but then I think the biggest problem with them is that I mean, they take a lot of steps to solve the problem, and that can vary depending upon the
the task.
problem and stuff,
Right.
compared to a neural network, which is it's like one shot, like one forward pass, and you get an answer. I
Yeah.
guess with this nature of neural network, which are like feed forward networks, that's how they are referred,
Right.
they became super popular, and probabilistic models, people started l- paying less attention to them. So at some point, there was also in between an interest in the community to bring them together. So the work that I did in that area is like trying to take probabilistic models, and then whatever typical inference algorithm is used to solve that probabilistic models, we would approximate that by saying, of course, this may require me to do 20 steps or 30 steps, depends on the problem, or depends upon the
Right.
parameter, depend upon the image. But I will just say I will only do 10 steps. I'll decide that. And
Right.
say that after 10 steps, I'm done. That's the only compute I would give to the probabilistic model. Then it fits into the natural paradigm of feed forward networks because now you know that it's a fixed 10-step
Right.
process.
Right.
Then if it's a fixed 10-step process, you can put one step after the other and call them 10 layers of a
Yeah.
network. So
Hmm.
that is what we did. We took some sort of probabilistic models, more like continuous Gaussian probabilistic models, and then said, oh, we'll take their inference and convert it into an unrolled network. And then this is a network, so I can just stack it to any other network.
Yeah.
So we did some works where like, okay, I'll have a standard convolutional neural network. It gives me something out, on top of which I will have some other network, which is like a random Gaussian, like probabilistic model network, and everything is again a deep network.
Hmm.
So that was like a way we kind of brought probabilistic models, approximated them as a neural network, and then merged with popular convolutional neural networks at that time, and
Right.
then said, "Oh, everything is a network." Then let's train the models. I
Hmm.
guess people can potentially do those sort of things or ideas on top of transformers also. Maybe some people are doing, but it's not a, I don't know, very catchy or like a primary
Right.
thing popular. It might be just because transformers are probably so good that they are doing it. And
Yeah.
if somebody says, "Oh, you are taking a probabilistic model, approximating into a deep network, why do you
Yeah.
want to do that?" Then if I am running 10 layers of a probabilistic model, I might just instead do a 10-layer transformer.
Yeah. Hmm.
So it's almost like, and transformers are probably more, they are like in terms of capacity,
More capable.
more
Right.
capable. So I guess it's just going in that direction. Maybe there, I mean, in the sense, what happens, I would say this, many times in the field when something is really working, everybody focuses on that. I'm
Right.
sure there may be other interesting things, even with probabilistic models and stuff, which people may probably are not paying attention to it because at least there is something that's working. Maybe someday somebody may suddenly do something, and
Right.
again, maybe the community may pay attention to it. But yeah,
As of right now, it's not in the
but that's
center.
not like a big focus
Right.
because the community is focusing a lot on this, which is, I would put it this way: back before transformer, before things, even if it was even before convolutional neural networks, a lot of focus in the community was on modeling. How do I
Hmm.
model something? What is the best neural network architecture? How do, given a problem, what type of machine learning model should I use?
Yeah.
Then I think now the trend is completely opposite. There is only one model, a universal model called
Yeah.
transformer.
Right. Right.
It's whether you are a vision person or a language person or you're working, it doesn't matter what you're working on, just one model. And it has pretty good capacity. If you have enough data, it'll learn very well. So
Right.
the modeling aspect or the training part is almost like converged to something, and people are focusing a lot on data.
Right.
There's a lot of work in the community around data because I don't know if it's belief that if I get the right data and a lot of it, this transformer model will learn.
Right. Right.
So
Like data's
my
the data's
attention to that. So
right.
it's a direction community is going in, but every time, usually after a few years, somebody will come up with something very different, new. I think
Right.
that,
That's very fast paced community, always changing.
yeah,
I was just interested in, just like a wrap up question. I was just interested in, any advice you had for students like I who are interested in pursuing a career in AI.
yeah. I mean, I would say it looks like, I mean, you guys are following latest work and stuff. So it's a good idea to, I mean, if you are actually interested in being in the research field and stuff, and I don't know, you're a high school student, so and you're going for colleges and like you want to work in these fields and topics, maybe it's good idea to do a bit of projects in this space. I don't know if that's what you guys do in your
Yeah,
club.
yeah, that,
Other
that
than
that's what
reading
we've done.
papers and like, yes, you get a good knowledge, but it would be good to actually build some models or actually have some GitHub repos. I see that that's something that gains a lot of traction. It's like if you have a GitHub repo where you train some models, you build something, you have shown it gives a lot of experience to you, and it also puts, I think it's a good thing on your CV where you can show that
Right.
See this my GitHub repo. I built all this code. I trained these type of models. I did these with these models.
Yeah.
That's a good thing. And I don't know if try. I don't know how often such opportunities arise, but if you can get a chance to do some internships,
Right. I know
especially in universities with professors or stuff like that, I would highly encourage to find those sort of things. I don't know how often industry has internships for high school kids, but
right. It's typically challenging. I think typically
yeah,
startups are more open, not really industry
yeah.
like
But definitely, I at least when I was in school, I used to see that schools have a lot of these programs for like
right.
to encourage. So try to find them and try to find some professors and who are working in these fields. Usually, actually, many of these things, in a sense, yeah, if you find a professor, typically professors will have their own like masters and PhD students, right? So if you can work with some of them,
Yeah.
yeah, that would be if you can find those type of opportunities, that would be really good CV and you'll get a lot of experience too.
Right. For
Yeah.
sure. Well, I really appreciate all of your insight. Learning about your research paper was amazing, and all of your thoughts on the future of computer vision and your advice was really interesting. I really thank you for your time.
Yeah, definitely. Actually, I have a few questions. I'm just curious. So how does it like, is there like in a school level, is there a course that teaches you a bit around about these topics, or is it just that you guys read books or
Uh,
read
yeah, yeah.
and
A lot of it is self-driven. So in our school we have an advanced curriculum, but the most they get to is teaching like introductory Java. There's not, we don't really progress past that. So a lot of the stuff that, reaching out to people like you and learning about this is more self-driven. Some people in our clubs are actively working with people. So we are located in New Hampshire, which is right next to Dartmouth University, which is it's in the area. So a lot of students will commute there, and that's one way we commute. Talk to those people. Obviously, it's hard to find industry internships, but that we do make active attempts outside of school. There's no real formal way of learning.
okay. So the actual machine concepts, I mean, since I mean the fact that you guys are reading papers and kind of to an extent are understanding them means some fundamental machine learning. How did you guys get fundamental ML knowledge? It's like online
Right.
course. Or,
So no, I wouldn't say online courses. So, what we do is, as part of college applications, typically people are interested in getting awards and all this stuff. So, as such, there are some high school science competitions, and uh, me personally, right, for my science competition this year, I worked with LSTMs and CNNs to make my project was more on like MRIs and forecasting the growth of tumors in the brain using some machine like standard machine learning models. So it's all like, just in an attempt to just build up projects and have fun with it. So yeah.
cool. Yeah. I mean, just I would also encourage you to look into. So there is another recent work from our group at Apple. It's called Mobile Clip.
Mhm.
I think the other thing is, and a good thing is that these days, even a lot of people, even from companies, when we build all these models with a lot of data, we are spending so much time and money and stuff in building these models. So it's good to open source them. And that's the trend you might have seen all this Google
Right.
Meta
The
and all.
llama stuff. Right.
Yeah, they open source all these models. So it would be also good to build some projects around that where you can take those models and then build things on top of them,
Right.
which I mean,
Right.
maybe
Some
more easier to do.
right. Some people in our group have they've tried to start contributing to the PyTorch repositories and stuff. I mean that's a little it's challenging, but it's
Yeah.
it's definitely worth an attempt. So
Yeah.
yeah.
Mm. Yes. So that's actually maybe that's another suggestion I would give. There's like a lot of this open sourcing happening now. If you follow this. papers or things that you'll find, and then maybe you can get those models and then do some cool stuff with it, or demos or things, or build some applications using them. For example, check out, I mean, if you do Google Clip, say Google Mobile Clip, you'll get the links. So these are like, you're familiar with clip models, right? This image
Right.
text model. So we have built some image text models, basically clip models, but they are very small, which you can run on your phones or any device, iPhones, iPads, everything. That was one of the main goals for us, that we wanted to build models which are small that can run on these devices, and all those models are open sourced. Maybe you can take those models and build some cool applications
Yeah,
with those,
yeah.
some of the projects. Just that.
For sure. Yeah. The open source models and just working on development of that is great experience. And like you
Yeah,
said, it could be good for your resume and CV
yeah,
too. So who
yeah, yeah.
knows? Right.
Hmm.
Yeah. Did you have any other questions for us?
Yeah, more like general questions to understand. So, is that like this is a club that you are like you run, or how does it work? Is it like enough motivated people that just pool and
Yeah, exactly that.
you
Yeah.
have like some, I don't know, teacher, professor, what do they call in school here?
Yeah, it's just just a teacher and typically like so I'm the president of our club at school. So, I was interested, so I talked to a teacher, but and then, we set up like an informal club. And then from there it's relatively easy because everyone in high school wants to do computers. So
Yeah,
it's
yeah,
just it just happened that everyone came to the first meeting. So it just they weren't able to join us today because everyone's in different places, but
yeah.
that everyone it just happens naturally because everyone's interested in it. So
That's good. Yeah,
yeah,
good. Yeah, good luck, and I don't know. Yeah, feel free to ping me in the future if you need any other information or anything from me.
yeah, of course. No, I really appreciate it. I mean, a lot of your insights were very very helpful, and I think a lot of members will be
Yeah.
very intrigued by
Cool.
some of this stuff. So thank you
Yeah,
so much. Have a great day.
me too. Bye.